our time zone. Karibu sana for, I'll say, the first webinar for the year. This is a webinar that we look forward to, have 1 to 3 talking about space debris. I know most of you have got a lot of questions, a lot of clarification, and this is the place to ask all those questions. We will try our best to answer those questions. Otherwise, karibu sana, and this is the Kenya Space Agency. We're hosting this webinar and Space Club. Yeah, so generally talk about Space Club. Space Club is, I will say, service that KSA gives to students, learners, whether you're in the university, whether you're in high school, whether you're in primary school, kindergarten. Yeah, so this is where we bring learners together just to interact. With a conversation where they have hands-on sessions, STEM related. But for that, we don't do it virtually. We have to be in the school. We have to be in a place where can speak one-on-one. Yeah, we have immersive learning. We have. I think that's the major thing that we do. Yeah, immersive learning in the aspect of AM sessions, in the aspect of robotics, in the aspect of building. Yeah, putting together a rocket with the materials that are available. Yeah, we call it a water rocket, just to understand the science, the physics behind how a rocket takes maybe a payload to space. Yeah, so generally Kenya Space Agency, our mandate as Aristotle is to promote, coordinate, and regulate all space-related activities. Yeah, so that's just an overview of the Kenya Space Agency. And the reason why we do this webinar is just to achieve one of our strategic goals, which is developing national capability when it comes to trying to create, to enhance, trying to create a space ecosystem in the country. That's why we have this webinar, to reach to those that we have not reached to the regions, also those who are maybe in diaspora but really want to hear about what is happening in Kenya. So karibuni sana. We have, sorry, I forgot to say my name. My name is Joanne Tane. I serve as Space Education and Awareness Officer. Yes, I am basically the person who gets to handle all your requests when you want to hear about space. Yeah, or about STEM in school, universities, colleges, or anywhere. Yeah. And on to our today's session, we have one of our own. His name is Jovian Store. He's has a background in aerospace engineering. He's the person, or rather the profession, who's going to explain to us really what is space debris, what's the science, what's the physics, all that. How did we get there, and what can we do to get out of where we've reached? So on to our presentation. Store, karibu sana. It's your turn. And for those who don't know karibu sana means welcome. Yeah, in Kiswahili. So on to Store. Thank you. If you have any questions before Store comes in, if you have a question, yeah, just drop it in the chat. And if you feel that you really need to speak, you really need to have more clarification about the question you asked, just raise your hand. We will unmute you and give you a chance. Anytime, if even though the presentation is going on, just raise your hand. We're here to listen to that question. All right, on to you, Store. Thank you. So we can't hear you.
Sorry about that. So thank you, Joanne, for this opportunity to speak about the Space Debris webinar. So thank you all the participants who made time to actually attend this webinar. So I'm going to proceed by sharing my screen. Thank you. Okay. So I hope you can all see my screen. Okay, so Welcome to the Space Debris webinar. So the overview of this webinar is basically going to touch on introduction to space debris. So basically, what is space debris? Where does it come from? And the effects. Then we're also going to talk about the risks of space debris, then methods of tracking space debris, then mitigation measures for space debris. Then there'll be a Q&A session. So introduction. So basically, I'm going to begin by what is a space debris. So basically, a space debris are just basically a collection of defunct objects orbiting the Earth. So they can be basically in an operational satellites, they can be rocket bodies, they can be fragments generated from explosions, collisions, and faulty payload assembly. So basically, there are two primary sources for space debris in Earth's orbit. So basically, from accidental and intentional breakups, which basically produce long-lived debris. And of course, the other primary source for space debris is basically intentional breakup during launch vehicle operations for the upper stage and other orbital stages for the spacecraft. So you can be able to see on my right here, we have basically all the sources of space debris, which include those tools by astronauts. We have all satellites which have launched a long time ago, probably 30 years old mission. Then we have parts of the rocket bodies, which include the upper stage for most of these payloads which are launched into orbit. And of course, we also have mission fragments which resulted from in-orbit collisions. So I'll go back to the history of space debris, which began in 1957 due to the launch of Sputnik 1. We all remember this one was a Soviet satellite that was launched in 1957. So it's part of the mission that resulted in the first stage for human-made orbital debris, with the first piece being the rocket stage that, of course, launched the artificial satellite, and the second source of the debris being basically the satellite itself. Then, of course, there's one other interesting aspect. We have the first in-orbital collisions between the Iridium satellite constellation and the Cosmos. So this one was the first accidental hypervelocity collision between two satellites, happened around 2009. And of course, the Iridium belonged to the US, which is an operational satellite. Then the Cosmos 2251 basically was an unfunctional satellite, belonged to the Russian. So of course, there's the issue of liability, because when you start talking about the international law, which is applicable to in-orbit collisions, basically it's derived from the 1967 Outer Space Treaty, and also the 1972 Liability Convention, whereby it states that under these treaties, the launching state is the one that is primarily responsible for all objects in orbit. So according to that common definition, then the question becomes that since Russia was the launching state for the Cosmos satellite, which was non-functional, and of course, the Iridium 33 wasn't registered in the United Nations Convention. So the question of liability comes about asking who is now the primary responsible for this in-orbit collision, and who's going to pay the other one. So that's another aspect that we're going to discuss here. Then, of course, we have this graph here basically shows Socrates. Socrates basically is a Celestrack, which is used to actually do predictions for in-orbit collision. So it can be able to basically show you in terms of minimum range in terms of separation between the two satellites, which of course are going to show you over an STK simulation. So basically, Socrates stands for Satellite Orbital Conjunction Reports, assessing threatening encounters in space. So also going to discuss that in the next slide. So the risks of space debris. So these risks are going to be divided into two. So one is going to focus on in-orbit operations. The other one is going to focus on re-entry effects of space debris. So we are all aware that the outer space is just an example of an extraterrestrial common resource. So it doesn't belong to any country or any sovereign country. So basically, it's a universal common resource. So the risk of space debris, I'm not sure if you're all aware of the Kessler syndrome, which is basically refers to a theoretical scenario, which was described by a NASA scientist called Donald J. Kessler in 1978. So it basically talks about cataclysmic reaction, where we have a chain reaction between collisions of orbiting assets. So basically, it says that in which the density of objects in low Earth orbit becomes high enough that collisions between these objects will continue to generate an increasing number of small fragments. So this becomes a completely, complex, progressing chain reaction. So what we do basically to be able to prevent this Kessler syndrome is that we talk about methods to actually mitigate space debris. We talk about ways to prevent conjunctions. By predicting conjunctions, basically conjunction stands for possible collisions between two satellites. So we're able to model that by modeling them as spheres, as you can be able to see. For example, in this video here, you can be able to see the red spheres. Basically, that shows that the minimum separation is basically less than 1 kilometer. So there's a possible conjunction. So what happens is that SpaceTrack sends you a request to be able to, it's called a traffic collision avoidance maneuver, like a request to actually be able to either change your orbit or either move up or move down to allow the other satellite operator to actually continue this orbit. But the question arises in terms of there's so many assumptions that we make when we are trying to do conjunction analysis. So basically, we model these physical objects as spheres in order to eliminate the need to have attitude information. So for satellite collision avoidance maneuver planning, you must take into account several factors. We're talking about weighing the risk of collision against the risk of performing a maneuver, because fuel is going to be used in terms of doing these evasive maneuvers. So the other aspect is, of course, it will shorten your operational lifetime. So you need to be able to do those trade-offs, either to increase your mission operational lifetime or you risk that by performing a maneuver. Of course, there's also going to be an aspect of mission degradation. So that is another thing that you must consider, because you're going to depart from your initial orbit. So that is something that you must consider, because for you to return to your nominal orbit, then you're going to have to actually do another maneuver. So that is, you're consuming fuel, which basically shortens your mission lifetime. So it's a lot of things that must happen. And this determination is based on when the secondary object transgresses the user-defined safety zone. So I'm able to show you here. So basically from here, the bottom here, you can be able to see the SpaceTrack, that is basically STK, Systems Toolkit interface, where you select your primary satellite, which becomes basically your primary vehicle, which you're trying to model against all other orbiting assets. So we have Taifa 1, basically Kenyan satellite, which you're trying to model with all respect to all other satellites, so STK, TLE, all of it. Then you're able to obtain such a report, which tells you have object P with the satellite catalog number. Then you have Taifa 1 with the satellite catalog number. It shows you the threshold of entry, the closest approach, the threshold exit. Then you're able to get the normal tangential crosstrack, which are basically the way you define this three-dimensional in order to avoid having to take into attitude information. Then it basically tells you the time of closest approach and also the relative velocity at the time of closest approach. So basically, since they're in low Earth orbit, the relative velocity will be the sum of the two velocities since they're coming into contact, which is about 15.12 kilometers per second. You can imagine the small fragments resulting from this collision. So these are something things that we need to consider. Then this upper interface is basically keep track. This is also another virtual telescope, which basically shows you all the orbiting assets, including space debris, rocket bodies, the payloads, special missions, and also, of course, satellite bodies and missiles. So basically, this shows you a lot of possible re-entries that might happen in the future. So the reason we do conjunction is to be able to actually predict imminent collisions and try to avoid them. So if a satellite operator does not have a method of actually doing an evasive maneuver or performing a collision avoidance maneuver, we look for the other operator, the satellite operator. We advise the other one to actually do either raise the orbit or lower the orbit. The same way aircrafts work with the traffic collision avoidance system, where when two aircrafts are coming in opposite direction and they are in the same altitude, so one must be able to go up, the other one to go down. So the threats basically include threats to spacecraft and astronauts in terms of micrometeorites and orbital debris, that is MMOD. Then, of course, increased collision probability, because there's increased probability of collision between two satellites, especially when the range of separation is very less. Then, of course, we have collision with operational satellites, so it poses a threat to orbiting assets. Then, of course, debris cloud expansion as a result of the Kessler syndrome. And of course, they hinder the space activities and make certain orbital regions unusable, because if you're launching constellation of satellites in low Earth orbit, and then of course you're crowding the orbit, so basically makes the orbit unusable for future space activities. Okay. So I'll continue to the next slide. So this is another risk of space debris, basically re-entry. So what goes up might as well come back down on top of you, and Yeah, so re-entry safety has for a long time been neglected under the wrong assumption that any re-entering object, there's always an assumption that even including massive spacecraft, they can always completely burn up through the atmosphere. But that is not really the case, because some continue surviving re-entry, especially if the spacecraft was not designed to have intentional breakup. So you can be able to say, this is what we actually anticipate. When you're doing the re-entry casualty risk analysis, you need to actually take into account the re-entry trajectory. You need to take into consideration the features of these fragments that are going to survive the ground in terms of mass, the size. The size comes into the aspect of radar cross-section. Then the material, what material is it made of? Because there's some material that can be able to withstand the aerodynamic hitting during re-entry. Then, of course, the casualty area of each fragment and the total casualty area, the total casualty probability to population, so the casualty risk. Of course, we tend to limit this in 1 in 10,000, of course, in terms of the risk to human casualty. Then, of course, the declared re-entry area and the safety re-entry area, which, of course, is defined by the inclination of this debris before re-entering the atmosphere. So what we do basically is that we take the catalog data from spacecraft. Then we feed it into an orbit propagator. You can have an AGI systems toolkit. You feed it into the orbit propagator, basically SGP4, then you're able to predict the lifetime prediction for that satellite, basically the orbital decay model, taking into account aspects of environmental modeling. So in terms of, you're talking about the drag, you're talking about, the re-entry angle, most of these things, they affect the, prediction of space debris when it's re-entering the atmosphere. Then, of course, we are assuming that most of the breakup will happen at about 78 kilometers. For integration altitude, this one is basically for propagation in terms of SGP4. So you take into account the mass, take into account the radar cross-section, you take into account the method that you're using to propagate, whether it's Rankuta, Kuta-Jakowski iterations, to be able to do this numerical analysis for the propagator. Then, of course, you calculate based on the epoch. So the spacecraft provides you the possible re-entry dates, and then you're able to take that catalog data. So the catalog data is basically the two-line element, TLE, which basically takes into consideration the different aspects of the space debris in terms of eccentricity, the inclination, the right ascension node. You're talking about the mean motion, mean anomaly, so those kind of stuff. Then you're able to feed it into the orbit propagator. So these are just some of the analysis tools that you can be able to use. So we have object-oriented survival analysis tool, which mostly used to model this, so that you can be able to actually anticipate something of this sort. Then you have the debris assessment software for NASA. Then you have the space atmospheric re-entry and the thermal breakup. Of course, these ones you can be able to register through the NASA technology transfer portal, and then you can be able to access this one. Then we have the AGI systems toolkit, which I'm going to show you. Then we have the space tracker.org, basically where the United States Joint Space Operation uses to monitor all orbiting space assets. So this is just some of the re-entry that have survived re-entry. Okay, so I'll talk about the incident that happened in Kenya. So the incident that happened in Kenya is one of those uncontrolled re-entry. So whereby we're talking about uncontrolled re-entry is where the space debris doesn't have any form of thrusting mechanism or any form of controlled descent. So basically, you cannot predict, because there's some sort of uncertainty in terms of estimation for the re-entry epoch, basically the re-entry trajectory, the re-entry time, the re-entry date. So most of this results from complicated shape, and of course, unknown attitude evolution of the re-entry object. For example, given that it was passing over the equator along Africa, where there is no space situational awareness, space infrastructure in terms of orbit telescopes, optical telescopes, and also ground-based radars. So it was impossible to actually be able to have updated attitude evolution for this object, and also due to sparse and inaccurate tracking data, of course, along the equator. In Africa, we lack those kind of space infrastructure to actually track and keep monitoring the space debris. And also in terms of biasness and stochastic inaccuracies from the computation of atmospheric densities. So what we are assuming is that during re-entry for these low space systems, they will re-enter at very shallow angles. So the assumption is that they will have to burn throughout the atmosphere. Then, of course, this debris, they will fall within a latitude band which is defined by an orbit inclination. So our assumption is that this object that fell over Kenya had a low orbital inclination. So we're talking about something closer to 0, but not 0, so around 0 to 10. So that is why, because if you look at the latitude band of Kenya, we're about plus or minus 4. So that means that the object definitely had a very low inclination when it was initially launched. So yeah, then of course the location for uncontrolled re-entry is unpredictable because the assumption is probably it could have fallen into the Indian Ocean or could have fallen in any other place. So that is something that somebody needs to take into account. And of course, the other aspect is that 10 to 40% of this mass must survive re-entry, and of course, the impacts definitely pose hazard. But in our case here, we had minimal effects in terms of actually affecting people, but of course, yeah. So the other aspect that I want to talk about is basically just, giving a light note that the people who are saying that it was India, it wasn't India because, for the PSLV, the C60 mission that was launched from Satish Dhawan Space Center, because Satish Dhawan Space Center basically is located at about 13.73 degrees north, that is the latitude, then the longitude is about 80.3. We are with assumptions is that the stage separations are going to happen over somewhere here. So basically, the probability that a stage separation happening over here coming to fall over here is impossible. So that's another thing. Then the other thing is that the recovered object is located far from this re-entry corridor. So the PSLV was launched about 10:15 p.m. That is Indian Standard Time, which basically correlates to 7:30 p.m. Eastern African Time. So the stage separation will have re-entered the atmosphere shortly after launch. So it is inconsistent because you're basically saying that the effect happened before the cause, which is impossible, ruling out the PSLV C60 mission for the docking as testing mechanism. And of course, the STK simulations confirm that all the PSLV C60 stage separations, they follow the planned flight path along this sun-synchronous. Sorry about that. So this is basically what happens in the systems toolkit modeling simulation. So basically, you can be able to see the launch trajectory flight path. So all of these, stage separations are going to happen over the territorial waters of closer to India and somewhere within this territory. So basically, this rules out the possibility of a space object or an upper stage from this mission to actually fall over Kenya. So how do we track and monitor space debris? So this is the aspect where we have something called space situational awareness, then which extends to space domain awareness. Then it can also extend to space traffic management. So SSA basically aims to monitor, track, and predict the resident space object positions, RSO, movements, and status. So understanding where satellites are, their status, where they're going to be in the future to enable space sustainability, basically to improve and minimize collision risks, and also predict satellite re-entries from those that have, probably decayed or their mission has come to end of life, and also mitigate the effect of space debris. And that is why we do space situational awareness. Basically, we try to track, monitor, and keep track, using several space ground-based space infrastructure and also orbiting assets, such as optical telescopes which are orbiting. Then, of course, when you further extend the SSA to monitor and, monitor the ownership and actions of military satellites, then you extend to something called the space domain awareness. So basically, this is the spacetrack.org, where basically you obtain all the TLE or the catalog data for each satellite and each space object that is currently in orbit that is being tracked by the US Space Track 1, that is the JSCO. So here you'll be able to get the source, the radar cross-section, the decay epoch, everything that you need, the country, the international designation for the satellite objects, the satellite's name, and also the NORAD CAT ID, which can be able to actually be able to tell you that these are the possible re-entries that happen between this date to this date. So from there, you're able to see which of those objects you can be able to actually determine. So from this, you can be able to actually tell what happened in Kenya. So basically, because SpaceTrack is I would say it's a data portal where you can be able to actually obtain all the catalog data for all the space objects. This one belongs to a European Space Agency. So of course, all of them obtain their data back from SpaceTrack. So you have the COSPA ID, the satellite number, the name, the reentry date, the uncertainty in terms of reentry, and then of course the mass of the object, and also the class. Is it a payload? Is it a rocket body? You know, those kind of stuff. Is it a rocket debris? Then from there, you're able to see, you know, the ground tracks, or not really ground, it's basically ground tracks, but basically it shows you the orbiting path for these objects. Yeah. And here we have the JAXA SSA system, which basically consists of the radar, optical telescopes, and an analysis system. So we have the radar, which basically scans. Then we have the optical telescopes, which is able to actually do tracking for geostationary orbits, while the radar does for low Earth orbit. And of course, you can also have some aspects of orbiting assets. So this is just one form of space infrastructure that we are looking into developing so that we can be able to have our own SSA capability within the equatorial region and also within the African region, so that we can also be able to update and contribute to space station awareness mitigation policies. Then, of course, this one belongs to Raytheon. So it's basically a NORIS orbital analysis toolsuit, which has the same interface as STK. So it's able to show you the ground path and also possible reentries and all the possible reentry latitude. So from the SpaceTrack back to SpaceTrack, you can be able to obtain something called TIP. Basically, that is the impact and prediction on message, which basically tells you or gives you unique set of data, which include the US space catalog number. You're talking about the the latitude of the predicted reentry, the longitude of predicted reentry, the orbital inclination. Mostly, this happens for those objects which have a potential, or they have a potential to actually cause a lot of human casualty. The debris has large mass in such a way that it can be able to actually survive reentry. For example, something like this, 440. You're talking about 440. That is massive. Definitely, it must survive reentry, most of it. Yeah. So then, as a general rule, radars are primarily used to characterize space debris population in low Earth orbit, whereas optical telescopes are used for more distance optical regions, such as the geostationary region. So you have the ground-based laser, which is basically used to pointing. Then you have the acquisition radar, which basically targets the debris, and then you're able to get the trajectory for the debris. Then, of course, debris tracking tools. You can have AGI Systems Toolkit. Then you have the SpaceTrack.org. Then you have KitTrack, which is basically a virtual telescope to do that. You have the NORStrack, which belongs to Raytheon, of course. That one you have to actually have partnership. This one is still part of ESA, but this one you can be able to access it once you create an account with them. Then space debris removal, ways to actually mitigate it. So how we do this is that you can be able to, categorize this into two broad categories. That is, those that curtail the generation of potential harmful space debris in the near term, and those that limit the generation over the long term. So the former one basically is going to involve the curtailment of the production of mission-related space debris and avoidance of breakups, while the other one, which was about basically having to limit the generation over the long term, is, you can have different aspects for future missions and past missions. For past missions, it's going to focus on active debris removal, while for future missions, we're talking about end-of-life services. So future missions, so basically you're talking about large constellations which need to retrieve their defunct satellites and replenish with new satellites. You're talking about Starlink satellite services and also other mega constellations which are currently in orbit. So for the launcher systems, then of course, active debris removal technologies will eventually apply to them to be able to actually remove the upper stages, which actually deploy satellites from the parking orbits to their final orbiting trajectory. So we have different ways of actually doing this. So one of them, and the efforts to actually do this, it's not about near-term profits. We're talking about you want to be able to extend the life of a satellite and be able to reduce the environmental impact of launching new platforms, and also mitigating the risk of failures in orbit and limiting the amount of space debris. So we have different methods. For example, we have the laser orbital debris removal method to actually be able to use a ground-based laser to actually point at a satellite to be able to deorbit it. So another one, you combine it with a space-based laser. So this one is able to actually do the space debris removal by actually forcing, the satellite to be able to burn up and actually be able to deorbit because of ablation product. So it's like a form of forced re-entry to be able to actually decay. And this is just basically the orbital mechanics. You have the velocity, tangential, we have the tangential velocity, then we have the radial velocity for the object, and then of course the laser beam, then this is basically the space debris. So you're basically forcing it to be able, this is the initial orbit, this is where you're trying to force it to actually be able to decay. So you have the perpendicular with the tangential velocity, then you have the normal velocity for the ablation products, and then it's able to deorbit. Then you have this other one where you actually basically use, it belongs to clean space. This is just another approach where you basically launch a vehicle, and the vehicle is able to actually eject or, eject the capturing mechanism to be able to actually approach rendezvous. So basically here you'll have two aspects. You'll have the chaser and the target vehicle, the same way as this one, where you have the chaser and this is the target. So once the chaser is able to actually attain the target, it's able to do a forced re-entry, which is basically the orbiting mechanism. Then to be able to extend the life of a satellite, talking about in-orbit servicing and also in-orbit assembly. So for in-orbit servicing is where, for example, you have a geostationary satellite and you do not want to launch another mission so that you can be able to actually take over the geostationary slot. What you do is that you launch another mission to actually extend the mission of the other satellite, where the mission robotic vehicle is able to actually dock with the other active satellite or the client satellite, as you can be able to call it. Then it's able to actually extend its life mission, providing more fuel or basically just keeping its orbit in terms of station keeping. Then we have another aspect of active space debris removal using a spiderweb space nets. So these are just proposals to actually do space debris removal in terms of active debris removal. Then we have the space debris mitigation. So we say there are two aspects. One is to be able to actually prevent harmful space debris in the near term, and the other one is to also limit their generation in the long term. So there's the Interagency Space Debris Coordination Committee, which works directly with the United Nations Office of Outer Space Affairs, basically the COPAS, Committee for Peaceful Outer Space Affairs. So basically they have this, documented debris mitigation guidelines, which ensures that all space operators must be able to actually follow to be able to ensure that we do not contribute to more space debris. One of them includes limiting space debris. Basically, you limit debris being released during normal operations for spacecrafts. Then the other aspect is about to minimize the potential for breakups in case for future missions. So for in potential breakups, we're talking about intentional breakups, where people design vehicles so that they can be able to actually break up during their orbital lifetime, which is of course generates more space debris, and we're trying to actually prevent Kessler syndrome. Yeah. The other is to be able to minimize the potential for breakups during operational phases. So here we're talking about spacecraft and launch vehicle orbital stages, which should be designed to avoid failure modes, and of course avoid leading to so what you need to do is you can be able to use different methods to actually do disposal and also passivation for the measures to actually execute and avoid intentional breakups. The other one is to be able to limit the probability of accidental collision in orbit. And this one is where we talk about employing methods to actually be able to respond to traffic collision avoidance requests and also collision avoidance maneuver request from SpaceTrack. So if I'm a satellite operator and SpaceTrack has sent me the traffic collision avoidance request to actually do an evasive maneuver, I need to ensure that in the near future, when I'm performing this evasive maneuver, I do not pose threat to another orbiting asset, another satellite in orbit that is currently also in orbit. Because when you change your nominal orbit, it means that you are moving to another orbit, and that also increases your chances of actually posing threat to another satellite in the near future. So what you do is basically you need to limit the probability of accidental collision in orbit. And by that, you integrate different forms of thrusters to actually be able to change your orbit. Then another one is to avoid intentional destruction and other harmful activities. All these are just guidelines which have been laid out by COPAS and IDAC. So when intentional breakups are necessary, then they should be conducted in sufficiently low altitudes to limit orbital lifetime resulting to fragments, because of course we understand that these orbiting assets, especially in low Earth orbit, they're going to undergo orbital decay. So when you are trying to do intentional destruction, you need to ensure that they are at very low altitude in such a way that they don't pose risks to other space operations. The other one is basically to minimize the potential of post-mission breakups which result from stored energy. So we're talking about passivation. This is where now you need to actually do some aspect of passivation. Basically, you find a way to remove all forms of stored energy in that spacecraft. So including residual propellants and compressed fluids and discharge of electrical storage devices, especially during end-of-life mission. Yeah, when you're trying to actually deorbit your spacecraft and decommission it. Then the other aspect is to actually limit the long-term presence of spacecraft and launchers orbital stages in low orbit region at the end of their mission. Because, for example, the re-entry that happened over Kenya, we're assuming is part of an upper stage launcher vehicle. So, what you should, spacecraft or launch providers should ensure is that the upper stages, they limit their presence so that they cannot be able to pose stress to other orbiting assets. So when making determinations regarding potential solutions to remove objects in LEO, you need to actually ensure that you do not pose risk during re-entry to people and property, and also due to environmental pollution, which is caused by hazard substance. Then, of course, the other aspect should be to limit long-term interference of spacecraft and launcher orbital stages within the geosynchronous Earth region after the end of their mission. Of course, you have to move it to a higher orbit, which is basically the graveyard orbit. So here we have more, like an extended ways to actually mitigate future space debris. So for example, we have the drag augmentation system for space debris mitigation, where basically you're using a fan to actually extend actually not to extend, but to increase the surface drag of the spacecraft. So when you increase the surface drag of the spacecraft, it means you're increasing the orbital drag, or you're increasing the orbital decay rate for the spacecraft. That's why these are just future, solutions to mitigate space debris in terms of end-of-life missions. So when the spacecraft has come to end of life, you send a signal or a command to actually, activate the fan module or the sail module to actually increase the surface area or the drag of the spacecraft. So from the drag augmentation, you're trying to increase drag to be able to actually force the spacecraft to decay. Then the other aspect is about robotic capture systems, which you have already talked about in the previous slide. Then, of course, we have space tags. So we have different ways. You can do catapult, where you basically just use a net to actually capture space debris and then force it through the atmosphere. Then you can also do harpooning. You harpoon the satellite, like basically throw an arrow, and then you're able to. That is weird. Anyway, and then you can also equip the satellite with deployable sails, basically, as I've said, to increase the drag and also force the vehicle to deorbit. Then the other aspect is about laser ablation, which we already talked about, using a ground-based laser, able to, basically irradiate the spacecraft with laser to actually, force it to deorbit. Then, of course, you design for demise. When you design for demise, it's basically you are designing in such a, like a fail-safe, in such a way that the vehicle intentionally breaks up during re-entry. So you basically design intentional weak links, introduce intentional weak links on the spacecraft structure in such a way that the vehicle is able to actually break up during re-entry, so that there is no surviving space objects from the re-entry, so that it doesn't pose threats to, property and also human, because the whole idea is to be able to reduce the threshold of human casualty to 1 in 10,000. Yeah. So thank you. This is the end of the webinar, and I'm also going to show you basically the collision avoidance advanced conjunction analysis tool that is used to do collision avoidance maneuvers for spacecraft. So I'm going to stop sharing, then I'm going to share the SDK platform. So I hope you can be able to see my screen. So right now I'm going to share the advanced conjunction analysis tool, which basically is for advocates. So what you do basically is that when you check the properties, I have global attributes, just a minute. So what you can be able to do is that you have the primary list for the vehicle. So you can be able to select, for example, you have if you are a satellite operator, or you're a country that has a constellation of satellites, either for EO, what you can do is that you select all those satellites as your primary list. then you're able to switch them to that side. Then you select the three, dimensions, your tangential, cross-track, and the normal. Then, of course, the secondary list will include all the other surfaces. So you'll select STK all, that is STK TLE all, for the remaining surfaces which are currently in orbit. Then you're able to compute. So it will basically be updating. That's why you can be able to see it's doing advanced conjunction analysis tool calculations. So fetching all the other secondaries in orbit. Then once it's done, you can actually be able to go back. Let's wait for it to compute. Can be able to see it's about 60% loading. So it takes time because it's basically updating this from the AGI database, which is linked to the spacetracker.org server. So basically able to actually update that one. Yeah. It's about to finish. Okay, so it's already updated. So what we go back here. Then start running the analysis. So then, of course, you can always zoom into your orbiting asset, which you have modeled as a sphere. And be able to see, go back. We see the one with the red one. Of course, when you go to the report, it can actually tell you. Yeah. Okay, and be able to see now that is a predicted conjunction. So we have less than 2 kilometers in terms of approach. Now at this point, you'd have probably received. What is that one? The red one. Fine. Already gone. So yeah, that's how it happens. So then on this other side, you can be able to see the ground tracks. So since Taifa 1 is basically a sun-synchronous orbit, so you'll be going from polar to polar. So it's just, and of course, there are other orbiting assets on this other side. Then what you do is that you come to the conjunction analysis tool, and then you're able to do the graphing. When you do the graphing, you're able to obtain different variables. So you have the secondary vehicle list, encounter warnings, close approach by timing, close approach by minimum separation. So I'll do close approach by minimum that one. Then now I can wait for the report to load. This one, you can be able to actually show you the primary vehicle, which is basically the satellite with the NORAD ID. Then it basically shows you the object name. So for example, this is a PSLV debris. So this one is a space debris that belongs to Polar Satellite Launch Vehicle for India. So it shows you that their orbit is intersecting and there's a minimum range of separation of about 0.2. So it must be probably that one that we saw because, yeah, it was approaching the one with the red. So it's intersecting. It means that since it's polar and also Taiwan is polar, so it's basically in a way they're intersecting. So it shows you all the close approach by minimum range for all the orbiting assets. I'm able to see the rocket body. I'm able to see Starlink, Cosmos, Object Space B, so many of that. And then you can still go to close approach by this. Then you're able to generate the report. So yeah, this basically shows you the satellite catalog number, the minimum separation, the minimum range, yeah, with all the dates. So with this, you can be able to actually design a model in such a way that that model can actually be able to guide you in terms of, just ensuring that the collision probability does not exceed your user-defined threshold for your orbiting asset. And of course, there are several courses of action that you can be able to take you as a primary satellite operator. For example, as the primary satellite operator for our Taifa satellite, then we if the secondary satellite does have an active way of being controlled in terms of thrusters, then the owner or the operator will be contacted by SpaceTech to actually ensure that they can be able to do a maneuver which is scheduled prior to time of closest approach, because you have the TCA. So time of closest approach. I could have generated this other link, this other report, but the problem is that it takes time. So with encounter warnings, it basically tells you the time of closest approach. You can be able to actually schedule a maneuver. Then, of course, this maneuver will basically involve just changing the primary satellite's attitude to be able to minimize the cross-section in which the other satellite is able to encounter it. So if I zoom back to the model, you can be able to see possible conjunctions, and most of them are intersecting, the ones with the yellow. The one for the red is the one that is basically poses a lot of threats. So that is what you need to be able to ensure. But as a final resort, an evasive maneuver can be warranted, but you need to ensure that you have planned accordingly to ensure that you take the initial factors which I mentioned, that you need to be able to weigh the risk of collision against the risk of performing that maneuver, because eventually you're going to consume propellant, which of course is going to shorten your mission lifetime. And of course, when you shorten your mission lifetime, your mission degradation is also going to be affected, because remember, you're departing from your designed orbit. So you're going to go to another orbit which is different from your nominal orbit. And for you to actually do another maneuver to actually return to your nominal orbit, then you're going to have to spend another amount of fuel, which basically means that your mission lifetime is going to be reduced. So what you need to ensure is that for a maneuver to be able to be done, you need to ensure that the secondary object has clearly, has overly transgressed the user-defined safety zone for your satellite. Yeah. So I think that is it. Stop sharing my screen. And yeah, back to the platform. Thank you.
Thank you, Stoa, for that presentation. A lot of new things to learn. Yeah. I hope each and every one of you has gotten something new from the presentation. Yeah, but before you give comments about the presentation and what you picked for the highlight, there's a question for you, Stoa. I think from Karanja. Yeah, so does this mean that Kenya has no spider webs, lasers, or any other special protection or removal mechanisms?
So the question about when Type-1 is likely to burn out, that is just a question of actually doing an orbit propagator for the decay model, taking into account for the lifetime of the satellite. So maybe what I can do is, let me do this again, just to show what I'm talking about. So from the tool, you have this. So I'm going to select this as our satellite. Then from here, you can be able to actually get everything you want. You have the attitude simulator, you have the lifetime, you have generation of TLE, close approach. So when you come to the lifetime, this is where you actually, you're able to do that. You take into account the satellite characteristics. Yeah, so drag area exposed to the sun, the mass, the atmospheric model, depending on what you want in terms of advanced, then you can actually be able to compute, but I see I've not really actually, fixed the correct parameters. Then from here, you can be able to use SGP4 to actually compute that, and you can be able to graph. So when you graph, it can be able to tell you the possible re-entry date, the possible decay epoch. Yeah. So basically, that's the lifetime tool. So for the decay, it will be, basically for a 3U nano satellite, the mission can go up to probably 5. That is extended. That is too extended. You over designed the satellite, but majorly supposed to be between 2.5 to around 3 years. So yeah, so timely around there, 2027, 2026, late, early 2027, depending on the lifetime model. I cannot actually comment on that. Yeah.
You
have a number of questions from Ian Kamori. I think he has 3. Yeah.
Okay, regarding the debris that fell in Makueni, well, it was tracked, but 1 week after being 1 week prior to re-entry, since along the equatorial region, especially along the equator, we lack the necessary space infrastructure to actually do active space situational awareness. So what we do is that we depend on catalog data from spacetrack.org. Then we use other off-the-shelf tools. Of course, we are using the ESA platform. Of course, with the NORIS, then we have the Keep Track. So we're able to actually monitor and keep track of, the objects. Because when you check the space track, the last, the last data, the TLE data, or the catalog data for this object that fell in Makueni, it was about 1 week. It's about 1 week old prior to re-entry. So yeah, but what we know is that what you can do when you go to SpaceTrack, you can actually get an updated version of the data where you actually take the last TLE and then you're able to propagate it and model it. So when you use the lifetime tool, you feed in the correct mass, you can actually be able to know the propagated, object. Because what you need to know is that an object that is surviving re-entry definitely has a radar cross section of more than 1 meter square, meaning its area, it's more than 1 meter square. So the ones that do not survive re-entry have a radar cross-section that is very less. And SpaceTrack, in terms of high interest, basically it labels that as no. It is not of higher interest. But for this object that re-entered Kenya, when you look at the tip message from SpaceTrack, it basically had an interest of yes, that is basically W, meaning that this was of high interest in terms of re-entry because there was a potential to be able to survive, because you're talking about something more than 200 kilograms, and you're talking about a satellite of roughly 10 kilograms, like I found about 4 kilograms, 5 kilograms there. That one definitely will not be able to survive re-entry. But an object as massive as more than 200 kilograms or more than 150 kilograms will definitely survive re-entry, even a small piece of it. Yeah. So do we know who owns the debris that fell in Makueni? Well, we do not know. But you can be able to actually, backtrack, like you do a backtrack and then you can be able to actually look at those objects of interest that re-entered from 28th to 31st, and then you can be able to do your own, assessment and, just like that. But I cannot comment on that. Thank you. How can AI be applied in preventing orbiting assets from colliding and in deorbiting assets? Okay, artificial intelligence. Well, artificial intelligence can be able to be used in terms of actually scheduling and having advanced algorithms which can be able to actually do an evasive maneuver when they sense there's an incoming, probably an. What you can do, you can actually, maybe you're talking about having a space situational awareness infrastructure in which you can be able to actually configure it with your satellite, so that when it, you receive conjunction analysis request or traffic collision avoidance request from SpaceTrack to actually do an evasive maneuver, then your satellite can be able to do that autonomously without you actually having to, interfere with dynamics. So it's able to assess. It's the same way aircrafts are able to do the traffic pollution avoidance system, where an aircraft is able to send a traffic pollution request to the other aircraft, telling the other aircraft to go down while the other aircraft to pull up. So it's just the same aspect. Yeah. Basically, to do autonomous collision avoidance maneuvers. Yeah.
So there's a question in Q&A area. There should be like, yeah, actually two, yes, from Karanja and okay.
Okay, for liability, I've seen somebody's talking about responsibility and liability for space debris. Well, space law, as the United Nations Office for Outer Space Affairs. So we're talking about the 1972 Liability Convention and the 1967 Outer Space Treaty.
So what we know is that under these treaties, the launching state is always responsible for the use of outer space and also for the objects that are currently in orbit. So the liability convention always dictates that for damages that occur in orbit, fault must always be determined. However, I understand that there are some aspects of legal definition which does not currently exist to cater for the context of liability convention. For example, if my satellite doesn't have a means of actually doing an active collision avoidance maneuver, and also the other operator doesn't have another method to actually do an evasive maneuver, and our two satellites are in a possible collision trajectory, and we just sit and we try to wish that they do not collide. But eventually, when they collide, what now happens? Do I start pointing to the other satellite operator that you are the one who who actually knocked me in orbit or collided with me in orbit? Because they have no other way of actually responding to the traffic collision avoidance request to either move up or move down. So I think all incidents which have happened to date in terms of in-orbit collisions that have resulted to potential claims under the convention, including the Iridium that I talked about and the Cosmos collision, all these collisions have been settled by the respective countries outside the convention, because the liability convention does not state somewhere where this operator is going to have to pay this other operator. So, for example, if I collide with another operator, for example, Starlink, but Starlink has an way of actually doing collision avoidance maneuver, is able to actually change its orbit. So I'm talking about another satellite that doesn't have method of actually doing or responding to this TCA request. So when these collisions happen, we'll basically meet aside, we put the liability convention aside, and then we talk, we agree that, we can be able to settle this as different, satellite operators. We say that this is what we have agreed. So I'll take part of this responsibility, you also take part of this responsibility. So, because it's not clearly defined, and that's why the liability convention needs to actually have a way to invoke these aspects of, compensation for in-orbit collisions. Yeah. Thank you. That's what I can say about the liability convention. Yeah.
There are two more still.
Joanna, I don't see any other question. I think the last one was from Arnold.
Maybe I can read it from Karanja. So does this mean that Kenya has no spider webs, lasers, or any other space protection or removal mechanisms?
Well, these are basically proposed methods by private companies to actually try and clean orbit. We have Astroscale, we have the CleanSpace. All of these private space entities are trying to actually bid to be able to get the contract to actually try and clean orbits, try to extend satellite operations, like to extend a mission for a satellite. So if I am a customer and you've come with the requirements, for example, you do not want to replace your geostationary communication satellite, you actually want to increase its lifetime mission, probably due to depletion of propellant or fuel. So what you do is that you contract me as a manufacturer, or me as a company or a private entity that actually does in-orbit servicing. So I will launch my spacecraft. My spacecraft will do all the necessary orbital maneuvers, chase target maneuvers, and it's able to actually dock with the vehicle. And then from there, we're able to extend the mission of the satellite. So we, as the Kenya Space Agency, our mandate is actually to regulate space activities. So for example, if you are a launch provider, for example, you are a SpaceX and you want to launch from Kenya, that's where we'll come in. We will actually come in and try to regulate the aspect of launch capability. So in terms of trying to clean orbit, that is not really part, but we are part of the voice that actually is trying to talk about, we are trying to also want to contribute to, to this aspect of space situation awareness in terms of mitigation for space debris by actually partnering and having international partnerships to develop tracking capability. Because the whole idea of this, this webinar is to actually
voice out that we as the agency are trying to actually develop localized SSA capabilities in Kenya and also surrounding regions in terms of actually being able to track and manage the risk posed by space debris. Because from the other video you saw, there's possible re-entries that are going to happen in future. Yeah, as long as the vehicle, the space debris or the space object has a very low inclination, there's a high probability that it's going to fall within a designated latitude belt. So if it has a low inclination between 0 to 10, then there's a high chance that you'll either fall over the ocean or over the land. So what we can be able to do as a country is to be able to prepare ourselves by having optical telescopes, ground-based radars, so that we can be able to actually monitor and keep track, so that we know something of this sort is going to come over, and we should be able to be prepared as a country in such a way that we can be able to offer early warning systems in terms of actually being able to advise the people who are going to be affected by being able to predict the actual re-entry latitude, predict the re-entry, the impact point for that space object in the near future. So that is what we can be able to do as a country. But trying to, and also pushing for this, this dialogue of actually being able to, push for future sustainability in terms of the use of outer space and also responsible use of outer space. Because as a space agency, we are going to perform in conformation with the Liability Convention. Because you see, when you as a country start becoming a spacefaring nation, then you must conform to these UN conventions, Liability Convention, Chicago Convention, United Nations Law of the Sea, of course, especially mostly for the launchers. Yeah, so that is the only aspect that I can talk about. But active debris removal, that is not really part of the scope of us in terms of space situational awareness. Our scope is going to focus on being able to develop the space situational awareness tracking capability. Yeah.
There are two more. Maybe this one. Are there any plans to operationalize the Malindi launch platform? I read that the equator is prime spot when it comes to getting cargo in orbit efficiently.
Well, I will not be able to comment on that, but what I would say is that we, as the Kenya Space Agency, we have long-term vision of actually being able to develop and operate an equatorial spaceport, so that we can be able to have access to different orbital market missions. We're talking about LEOs and synchronous orbits. We're talking about equatorial orbits. We're talking about geostationary orbits. You can also do interplanetary missions. So yeah, and also because we have a lot of downrange safety in terms of territorial waters, so talk about the Indian Ocean. So yeah, it's lucrative or it's efficient to actually launch from the equator, because at 0 degrees at the equator, you're already traveling at about 456 meters per second. When you factor that into your fuel budget for the launcher, then it means that your launcher is able to deliver more payload. Because the analogy is, if you've been in a launcher optimization class or a lecture, you'll understand that the launch site latitude always influences the performance of a launcher. And that's why many countries try to find a way of having an equatorial spaceport. Because when you have your launch site latitude as small as possible, closer to 0, it means that your launcher performance to GTO, that is geostationary transfer orbit, increases, because you're able to bring more payload at the expense of fuel, because almost more than 90% of our launcher is basically fuel. So if you can be able to actually do a trade-off between fuel efficiency and payload capacity, then it means launching at the equator is more beneficial. So talking about the refurbishment of Malindi launch pad, I cannot be able to comment on that, but what I would say is that we are planning to develop an equatorial spaceport in the near future, yeah, which can be able to actually do this launch missions from Kenya. Yeah. Because the Malindi launch pad has been there for more than 60 years. Kenya used to be the space race for a long time, but people don't realize that. Because the space race happened it started around 1957 there with the Sputnik Sputnik launch. Right now, then we had the Malindi, launch activities starting off from the 1960s up through the 1980s, early 1990s, and then from there, the station of the launch pad was decommissioned So refurbishing an old, 60-year-old launch pad is a bit difficult because you're talking about a lot of issues in terms of floods, high sea tides. So you'd rather have an inland an inland spaceport where you can actually launch next to the ocean. Because of anything, you can actually, do a launch abort system, then you're able to destroy your launcher over the territorial water. So an inland will be more better than, sea platform. Yeah.
Last one, I think, do space body emissions contribute to carbon levels on Earth?
That's a tough one. Do space body emissions contribute to carbon levels on Earth? Well, I'm not really an enthusiast of climate. Maybe this one I'll give it to Olivia. Olivia is also an aerospace engineer. She can comment on this. Well, I would say it's quite impossible because, okay, probably because it's highly improbable because given the, but what I would say is that launch activities do contribute to, this aspect of greenhouse effect because of the launch emissions from the propellants which are being used in these launch vehicles. But for space body emissions contributing to carbon levels on Earth, I don't think that is possible because, we have different levels of the atmosphere from, troposphere going up to stratosphere, going up to thermosphere, when you go ionosphere. So it's impossible to actually have those contribute to carbon levels on Earth. But what I can say is that launch activities also do contribute to this aspect of climate change and also, environmental pollution. And that is why for somebody to actually be able to conduct launch activities, they must actually have conducted an environmental feasibility study. So NEMA will come into play because they say, you're polluting in the air, you're affecting climate because of, these greenhouse effect gases which result from some of these different types of propellants which are used in launchers. So that will be my answer to that. Yeah. But I don't think it's probably that they contribute to carbon levels on Earth.
Okay, no more questions. I think we end there. It's 10 minutes past the time we intended to end. So thank you so much for making time to be here and just to learn 1, 2, 3 about space debris. I hope you know something about what is happening in space, beyond the skies. Yeah. So, okay. Okay, thank you. Thank you. Okay, I don't know your full name, but thank you. So I've posted some
So, thank you so much. Sorry about that. For attending. I think I've posted something in the chat. This is Joanne still. About an event happening in Karen Waterfront. So there is quite a spectacular day for those who are interested in astronomy, where we have 6 planets forming something like a line. It's not exactly a straight line, but something that you can see like I think 4 planets. You're able to see them with naked eye, but the rest you'll have to use a telescope or a binocular. So if you have time, please make your way to Karen. Would love to see you there. So once again, asante. Until next time. See you.